Yes, it's on. So, good morning. As you know very well, if you really want something, the exact opposite happens. Every time when I try to squeeze some extra material in the last minutes, it's messy. So today we have plenty of time. Let's go decimo. Let's go slowly. Same reaction. We need to make sure we know how to calculate the products of any reaction. We're going to do more because this is just a prelude, just the first step for the next step, calculating energy release. So, carbon, number 6 in the periodic table, minus an electron which has almost no mass, elementary charge is -1, and the law of conservation of electric charge says total charge before the reaction should be equal to the total charge after the reaction. So now, next step. Slow down. Next step, subtraction. Next step, calculation. Next step, searching the periodic table. Found nitrogen. Next step, law of conservation of energy. In this situation, it says that total atomic mass number before the reaction should be equal to the total atomic mass number after the reaction. Algebra, arithmetics, done. That's how we approach every single reaction. Now, the most important part of the reasoning starts happening. Now we have to talk about energy. And now we have to answer this question. Which essentially represents the core, the most important part of the reasoning for any problem like that, for any problem on calculating the energy before something had happened and after. Just a sec. Okay, that's official. I'm getting rid of Firefox. They change it. A new update, every new update makes it worse and worse. All right, so this is a question about history of physics. Nothing else. It's about traditions. Chemists and physicists together have spent decades for measuring atomic masses of all known isotopes. So what did they measure? Atomic masses. They tabulated atomic masses. And they said, well, we've measured atomic masses. Anybody who needs a nuclear mass should be smart enough to subtract mass of electrons. That's it. It's just a tradition. But we have to follow that tradition. So the reaction and following reactions describe what is happening to a nucleus. That's why we call them nuclear. However, the numbers which presented to us are atomic. And the difference between a mass of an atom and the mass of a nucleus is literally difference. Subtraction is equal to the mass of the electrons orbiting that nucleus. That's it. So this is something just to remember. We cannot change it. It's been a tradition for years. And now we know what to do for this reaction or for any other following reaction. We cannot use these numbers directly because all those numbers, well, at least numbers related to an atom, to an element from a periodic table, all those numbers represent the mass of an atom, atomic mass. But if we need to calculate the energy released, and energy released, we know this term represents the amount of kinetic energy for each dot particle, for each remnant particle, a piece of the original nucleus. That's it. So now it's a very straightforward problem. So again, we have a process, and we always can relate everything. Actually, not just law of conservation of charge or law of conservation of energy can be used, also law of conservation of linear momentum. But we don't have to do that. Here we just need to use the equation which relates energy and mass of anything if we measure energy in mega electron volts and measure mass in atomic units. We could have used international system of units, joules and kilograms. In that case, we would have to use c squared. Why would we do that? Anyway, so before, we have only one element, and the mass of the nucleus of that element supposed to be equal to the atomic mass of that element minus the mass of all electrons orbiting, and how many electrons do circle in carbon. How many electrons circle in carbon? Same number as protons, same number as the number of elements in the periodic table. That's done after, well, Technically, we have three particles. If we go from right to left, we neglect any energy associated with neutrino. That's not a neutron, that's a neutrino, a Greek letter nu. It has some energy, but much, much, much less than all other parts, so we neglect it. So what's left? After it has two parts, we should use nuclear mass of this element, and we need the mass of that particle, which we call electron. So what's next step? The nuclear mass is equal to atomic mass of the same element minus the total mass of all electrons circling the nucleus. So how many electrons circle the nucleus in nitrogen? 7. Same number as protons. And we still need to keep electron. We still need to keep this. So now we need to calculate the difference. The difference tells us what people call mass deficit or mass defect. And that's spontaneous reaction. More mass initially, less mass after. In general, we can calculate magnitude of. So atomic of this minus 6 electron masses minus, well, this is what we could have called the mass on the left hand side of the reaction equation. Now we got to subtract the total mass of after the reaction had happened. So we just have to copy the whole thing. Atomic mass, minus 7 electron masses, but plus back 1 electron mass. Now we need to simplify this by opening all the parentheses. Do I have an extra slide? No. So I'm going to add an extra slide. So that's what we are calculating. Atomic minus 6 electron masses. Now minus atomic for the nitrogen 14. Now minus makes it plus 7 electron masses. And down. The transition is purely mathematical. So first of all, these parentheses don't make any difference. We can just take them out by, well, here. So these parentheses make difference. So if we take them out, this plus becomes a minus, this minus becomes a plus, this plus becomes a minus. That's what I did. However, what we can see now is, what do we see? Because in my mind, and I hope in yours too, every time when we write something, we always ask the same question. What can we do now? How can we make it simpler? Can we make it simpler? Mathematically simpler. The electron mass enters this expression several times, so it's a common factor, and we can make it simpler. And the result is (14.003241). (14.003074). So the energy release will be equal to this. Good at Thursday, I don't have to write anything accurately, even force. Millions of electron volts. 14.14.000033. So 241 minus 0.74. Energy released per reaction. Yes, so it's per one reaction. If we had more reactions like that, that would provide more energy released. Someone should already have a number, so we can write it down. And if that number would be wrong, we could blame that person. Who's brave enough? Please tell your number. This is a safe place. That delta M? Zero point 16. Thank you. We will see soon that some reactions provide much, much larger energy release. But from now on, any reaction can be treated in exactly the same approach. For example, beta plus decay. I'm going to give you 44 seconds to pull up the WebAssign, pick an answer, enter the answer. Because again, we just have to apply straightforwardly law of conservation of electric charge and a law of conservation of energy. And Z is supposed to be equal to 1 plus a question mark, and A is supposed to be equal to 0 plus, actually it's not even a question. Yeah. So this question mark is supposed to be equal to Z minus 1. That's supposed to be the answer. That's again just the prelude. Now we have to calculate the energy release, and to do that we need a specific reaction, nitrogen 7. So this is a positron. There is no special letter for the positron except beta. So we ignore the presence of a neutrino. A brand new neutrino detector has been recently placed in Germany. The place from where it was built to where it was located finally is about 400 kilometers away. but it took about a year to make it travel several thousand kilometers to bring it there. Because to detect neutrino, the detector has to be huge, and even slight tremor might break it down. It has 10 meters in diameter. It's cost hundreds of millions of dollars, so they couldn't move it straight. They had to move it using rivers, water, to bring it back to the destination. But we neglect this. For us, it's not important. So, what is important? This is supposed to be 6 carbon, 13, also not stable isotope. It will decay eventually again. And to calculate the energy, we just need to apply the same approach. Numbers on the screen present, what do they present? What type of masses? Atomic. That's it. So, delta M, I'm going to do delta M directly. That's supposed to be the atomic mass minus atomic mass of this element minus total mass of electrons orbiting. So 7 electron masses. And done with the left, minus first atomic mass of this element minus 6 electron masses. And a beta particle, again, is a particle which has the positive charge, but same mass as electron has. So 1 electron mass. Now we have to again simplify this by taking parentheses out. Atomic mass. Atomic. Minus 7 electron masses. Now minus atomic plus 6 minus 1. And again, we can simplify this equation because we have 3 terms with a common factor. Atomic minus another atomic. Now, minus 7 minus 1 plus 6, that gives left 2 electron masses, which are supposed to be subtracted. So there is a difference between different reactions. Sometimes the total number of electron masses before and after cancel each other out, sometimes not. We will see that this is the only reaction important to us when electron masses matter. There's one more reaction we're going to talk about today, alpha decay. And for that reaction, electron masses don't matter. And of course, this equation doesn't depend on the actual elements. It doesn't really matter what kind of element is involved. Yeah? The equation will be the same. Well, and if we finish the calculation, we get slightly different result. Now, what do you say about alpha decay? Because I need time to drink coffee. All right. I think I need time to drink more coffee. Where is the gentleman who used to be sitting with you, and for 2 days I don't see him anymore? He should have sent in an email. Please tell me that he should send me an email. Thanks. Go ahead, I'm just killing time. I have nothing to do right now. Things when I have nothing to do, not really good for this room. Watching movies, reading books. Again, at this point, I would expect, well, at least my hope is, that I will have finally 2 questions with 100% correct answers. There isn't much to think about, right? That's supposed to be 2, and that's supposed to be 4. Because if we add this number with that number, we should get this number. If we add this number with this number, we should get this number, according to 2 laws of conservation. So I don't want to. It is the. Go away. I don't want to look inside the Firefox. I want to believe everybody gave the correct answer. And if you didn't, ask yourself why. Now, so this is a very important example of this reaction, one of the most studied in the world, because a similar, and this particular reaction has been used for the Rutherford Experiment. Yeah, you could imagine this is a nucleus of a gold atom, yeah, thin gold film, and alpha particles traveling. And when they get very close, they get reflected back. And the Thomson models, go ahead, shoot. Cannot explain the reflection back. It's like using a machine gun and shooting through the cloud. Nothing going to happen. So this reaction was crucial for establishing quantum mechanics. But of course, if we wanted to, we could apply exactly the same approach to calculate the energy release in this reaction. And if we look at the left-hand side of this equation, and if we look at the right-hand side of this equation, we don't even see any beta particles. And if beta particle is not a part of the reaction, the number of electrons we have to subtract on the left will be equal to the total number of electrons we have to subtract on the right. And electrons will not matter. But if we calculate the energy release, is large. This reaction is kind of very slow. If we would use a different isotope of uranium, we could have a very, very much faster reaction, uranium-235. So, but again, the energy really is higher than any we've seen before. Now, that's not a question. Yeah? This is a definition of a new type of reaction, an induced reaction. So we use this word decay usually when a nucleus spontaneously decays. Some atoms are stable, or it takes too much time for them to decay, so we want to speed it up. And to do that, we just make it collide with something fast. We could use alpha particles to shoot, but alpha particles have a charge, so they be repelled. The best way to excite a nucleus is to shoot a neutron, because neutron has no charge, so it's not being repelled, so it actually can penetrate inside the nucleus and it explodes. In that case, we say a nuclear reaction is happening. And for every nuclear reaction, of course, we can always apply the same laws. For example, here, the charge 0 plus 5 supposed to be equal to something plus 2. What it should be equal to? 3. 1 plus 10 should be equal to something plus 4. 11 minus 4, 7. 3, lithium. Gamma has no charge, has practically no mass, has some energy. Energy enough to actually penetrate inside a nucleus and excite it. So, but it doesn't change the nucleus. It gets excited and then it decays. In what? Well, 1 proton flies away. What's left? 12 minus 1, 11. 25 minus 1, 24. 11. Zero, 0. So 7, 14. Nitrogen. But since we had to induce this reaction, so if we would calculate the mass before the reaction just for this element and for those elements, the mass would have been different. But now this mass would be less than that. So we have to put some extra energy inside that nucleus to make it excited, and then it decays. All right. Yeah, I had a slide. All right. Now, the history of study reactions like that is actually very, very interesting. In 1945, Russia, Germany, and US were racing for developing the atomic bomb. Who would do it first? And everything is based on a very simple idea. If you excite a nucleus, it can decay and can provide a very large amount of energy. And if you have a large sample of radioactive material, 1 neutron, for example, can excite 1 nucleus, but that nucleus, when it decays, it also provides some more neutrons, and those extra neutrons can collide with other nucleons, and they'll decay very quickly, and give more and more additional neutrons. So it happens in geometrical progression. And I actually have atomic bomb right here, right now. I have it preserved. It's very easy to trigger. And we don't want to do that. We want to survive, right? Now, the standard disclaimer, I have no idea what's going to happen. Meaning, I haven't done it in this particular version before. I just want to try an experiment. I had to guard it. Don't breathe. Don't say a word. You know, even a mouse can trigger a mouse trap. Now, that's only a part of the demonstration. Now I have to charge it. I could preset them before the lecture, but I couldn't preset the balls before because I wouldn't be able to move it. And I can't ask anyone for help because, well, I just don't trust anybody for this. This is why you go to study. That's what diploma is about. You wouldn't be able to do it without a high, at least high school diploma. Years of practice, hours of charging, minutes. You don't want to be killed, right? So we need a dome. Now we need a charger. Anybody has a knife to cut the tension? Okay. So this is a neutron which should induce this reaction. It's not going to be loud. Hours of work for a second of enjoyment. You can keep it. I've got more. Well, I like this demonstration because it really demonstrates the chain reaction. It happens very, very quickly. And by the way, I'm planning on uploading all the videos on YouTube. So if you ever feel down, you can watch this video and imagine me setting up those traps. Well, so that's how atomic bomb would work. To prevent that from happening, we need to manage the number of neutrons which reach the next nucleus. So we have to be able to absorb unnecessary neutrons, and well, we have to use special materials. One of the best is beryllium. Every atomic plant has beryllium rods. They put it in or out to manage the number of neutrons. And in that case, we can manage the energy release. We can use it to generate energy. So this is the reactor. Those particles which we observe after the induced nuclear decay, they travel very fast because they have very high kinetic energy. So what they do? Well, we need a tank with water. Those particles travel through that tank with water, and they give away that energy. Water becomes hotter and hotter. Eventually it starts boiling, and we can use that vapor to spin a turbine, and we attach generator. Generator spins, generates energy, and here we are, we use it. And yes, atomic bomb is dangerous, yes. Accidents might happen, but there is no way to escape using atomic energy. Eventually, all non-renewable energy sources will not be renewable. So it's inevitable. There is another source of energy which happens outside of the Earth so far. If we take two light nuclei, like two helium atoms, or two isotopes of hydrogen, a deuterium and tritium, and we collide them, if we're able to make them bring to each other very, very close, they start interact with each other, and then they explode again, and the energy release in that situation is much larger than the energy release during any known decay. So that's what is happening inside every active star in the sun. The reaction like that so far cannot be managed. So far, all we can do is make a bomb. So the energy release, if we could manage just 1 mole of deuterium, that would give us 2 10 to the 12th joules of energy. Well, people do work on different ways to manage that energy, but so far, the only way to use it is an explosion. And 5 or 6 things like that enough to destroy the whole Earth. I'm not sure if it's reassuring. The reassuring part is it hasn't happened yet, but crazy people do go to power sometimes, so we have to be very, very attentive. Now, as we have learned, there is a big difference between quantum world and classical world. For example, in the classical world, a particle which is in a potential well or actual well cannot escape it on its own. If the energy of the particle, total energy, is less than the maximum energy of the well, maximum potential energy, it remains inside forever. We have to use an external force, an additional energy to make it out. In a quantum world, actually, even if the total energy of a particle is less than the maximum potential energy of the system, there is a chance. A chance means mathematically calculatable probability and physically measurable probability of this particle, which is right now, right here, to get out. This phenomenon led to some Nobel Prizes, and we call it tunneling. It's a word. No one really knows what's happening. It doesn't have a drill. It doesn't drill a hole to make a tunnel. It just one moment is here, second moment is there. And that's what every decay is about. The alpha decay, Georgy Gamow developed the theory based on the tunneling principle, and then other decays. So it's here and it's out. But for every decay, there is a certain time when it happens, and that time is related to the probability of this to happen. But also, many ideas developed in physics might be useful for everyday life, at least for me. For example, I ask myself once in a while, what kind of a particle am I? Am I a classical particle? I reach the barrier and then bounce back, or am I a quantum particle? Have a chance to tunnel through. And here we are at the end of the tunnel. We have finished the course, completed, landed across the ocean. Next stop is Moon, Mars. So there's a lot of time for Q's and A's, but I want to present a standard note at the end of the course I've been presenting for years. Your evaluations, whether you like it or not, don't matter. There's only one person who reads them. There's another person who looks at the average number for the course. If that average is between like 2 and 4, no one cares about anything. So if you want to make a difference, you can put your evaluation in the open. But if you do that, please be specific, because if you say something like, oh, I liked it or I hated it, it doesn't help anybody. If you want to be specific, say something like, if you want to take this course, be prepared 1, 2, 3, 4, 5. If you hate something like doing in your life, don't ever take this course. But even this might be soon probably irrelevant, because if everything goes according to my plan, you're going to be my last students. That's why I want to give you, and only you, one more note. I've never done it before. I'm never going to do it again. You may have noticed, or maybe not, but this country is changing, because all countries are changing, because the world is changing. It's inevitable. Globalization, technology, robotization will affect every individual. How? No one knows, but it will. We'll be losers, we'll be winners. It depends on decisions which political elite will make. So watch out. Don't disengage. Very soon, thinking ability will become the commodity #1 in the whole world. Use it. It's too late for me. I already alienated everyone I could. But it's not too late for you yet. Now, physics. Questions? I am done. I can just walk out right now if you don't have any questions. Yes?
So there was a question on the homework where a thin film suspended in air, and it was asking at what wavelength will visible light be
On both sides?
on both sides of air?
All right, first of all, if it's suspended in the air, I still would draw it horizontally because that's how I see it. And first, every situation related to a thin film interference should be complemented with a picture because it helps to understand what is happening, and we have air, film. And I have no idea right now what question might be about because it is irrelevant. If it's a thin film interference, I know there's a first medium, there is another medium, and there's film. And we always have two interfaces, and delta T and delta B, those factors, phase change related terms, depend on relationships between the indices of refraction. And for delta T, well, first of all, we need to know a rule. A rule says that we only have two choices, and the choice depends on above, below, on two numbers. So in this situation, I immediately can conclude this is supposed to be air, so it's supposed to be a half of a wavelength. That's supposed to be film error 0. And now we know that effective path length difference is supposed to be equal to this. In this particular case, it becomes equal to this, where T represents the thickness of the film at the location of the interference. And only now we can start looking at what are we looking for. And that depends on if we see bright or dark things. So what do we see? What are we looking for? Fully constructive means we have to set effective path length difference to this. Now we have two equations, and we need to write them as one. And now we have to solve it for wherever we need to solve. Even now, even at this point, we're not searching for anything specific. We just used the fact constructive, so it was bright. So what are we looking for? And for this equation, we only have two options to choose from. We may be looking for the wavelength or for the thickness. That's it. Wavelength in the visible spectrum. So what do we know about the wavelength of light in the visible spectrum? First of all, which is very important, and sometimes people might forget about it, the wavelength is supposed to be used. The wavelength used in this equation is supposed to be calculated like this. So the equation we want to use should be like this. And we have to solve it for lambda, because we know that for the visible spectrum in air, that's important, A, visible. Visible is too long. In air, the limits about 400 nanometers and 700 nanometers. So if you solve this equation, 2t I need, so 2t, so let's go over here, lambda, actually I have to divide, I need to divide, so 2t, and m over n minus 1 over 2n, two t, I don't like many fraction bars, times 2n times 2n, 2m minus 1 for thickness index in a film, 2m minus 1. Now we have to start checking, because this is where we can't know the exact value of m, because first of all, for different thickness, we may observe exactly the same phenomenon. So there is not just one, there are many solutions always for a thin film interference. But in this particular situation, when we know the thickness, we just have to plug in numbers again and again and again until the result for the wavelength fits the visible spectrum. M equals 0 gives a negative wavelength out. M equals 1 gives too short, ultraviolet out. Usually it's M equals 2 or 3, which will give you the wavelength which fits the limits of the visible spectrum. Please, questions? Yes?
In the question we did in class for the minimum energy a photon needs in order to ionize a hydrogen atom, we said it so that the new energy was 0, and I didn't understand why that would be enough to ionize.
Ionization means that an electron is moved so far that it's not being attracted anymore. Theoretically, for any distance, for any given distance between two charges, that's a positive charge, a negative charge, force is not 0, theoretically. Theoretically, we need to set distance between the charges to infinity in order to set them free from each other. However, that would make everything to be equal to 0, not just the force. So in reality, of course, so this is just a mathematical expression. In reality, the distance when electron doesn't feel the presence of the proton anymore is not infinitely large, it's very small. But we always use some abstracts, like if we needed to calculate the energy of a satellite, it should have to fly away. We used exactly the same approach. We set the distance to the infinity. Of course, in reality, as long as it reaches the edge of the solar system and starts flying away, that's it. But when distance is infinitely large, everything is 0. That's the minimum amount of energy required. Because in this situation, or in that situation, doesn't really matter which situation we're considering, the word minimum says kinetic energy is also 0. It flies away and travels slower and slower and slower and slower and slower. So it stops. It is at rest at infinity. So no motion, no speed anymore. But if the actual kinetic energy of a photon would be higher than required, in that case, it would escape and still would travel, keeping some constant velocity. Did it help? So, yeah, well, for the potential energy, that also becomes 0. And for the kinetic energy, is 0 because we are looking for the minimum amount of energy required. So everything is 0. Total energy is 0. If you're not asking questions, I'm going to do this. If you want to stop this, you have to raise a hand. That's it. We still have like half an hour. And I still have some coffee to drink, so. You should have prepared the questions. Yeah. I emailed you yesterday, please prepare questions. I begged you for questions.
Can you give a good explanation as to why energy is quantized without using wave function?
No?
So we just have to accept that.
Yes? You know some things just like that, like the name our parents gave us. There is an equation, you solve it, it gives you answers. Those answers turns out to be discrete. That equation, Schrödinger's equation, explains many, many experimental results. So we believe it works until something happens, and I think new experiments will show that equation is not very accurate. We just use it. And mathematics of that equation, differential equation, ambiguous. The solutions exist only for certain values of those quantities. For other values, it doesn't exist. The question is why? We don't have the answer to that question. Well, some people do. They think they do. But in general, no, it's just a fact.
For the test, what units will we have to use? Because we started using some units that aren't SI units for the last few things that we did.
You can use any units, but you just have to be clear what units you're using. The rule is, if you use international system of units, you don't have to write the unit. It's assumed if you use other units, you have to write those units. International system of units includes seconds, kilograms, joules, meters. All other units, if you use them, should be shown explicitly.
Atomic mass units are not part of the SI system.
No, it's U. It has to be same as electron volts or mega electron volts or nanometers. You wouldn't write a number assuming millimeters without writing a millimeter. No. So same works for all except kilograms, seconds, joules, meters, and I think, well, maybe watts, meters per second. That's most common units. So, are we done? I guess we are. See you tomorrow. You know where? You know where. You know when. That's it. Same room. Same room. Same time.
All right. Starbucks?
I'm willing to, but then I have to do the air versus what we did on the homework. Figure out.
What's your next step? Where do you stand?
If I like go through everything by
You're
myself.
more to the left, but what's your?
Politically, I don't think that's the right word. I think what's missing in all of this
Drink
is
more
reason.
tea.
That's it.
Caffeine life.
I know.
On both sides.
Matcha. It has like the same amount of caffeine.
Oh, it's nothing to do with caffeine for me. I just love this taste.
Really?
Coffee's my happy.
I didn't
I
love
get a
the
little bit of
taste as
dogma
much as I
without
love the
trying to
taste.
I also like tea. I have tea in the afternoon.
things of the day. Things change.
Coffee makes my morning okay.
People can't accept the fact that things change. Old models don't work anymore. They just don't.
Alright.
You gotta start from scratch. And when you have to start from scratch,
Thank you,
everything's
Professor.
on the table.
Thank you.
Everything. Thank you. So, that's what I don't see. I don't see people who can we forget everything. Let's start from scratch. Let's rethink things. Only things what matters now. What do we want to achieve? And we have to say it's either, first of all, everyone says we need the fair society. Opinion. That's supposed to be the first discussion. What does this word fair mean now? Then starting from that, whatever happens, happens. It's unpredictable. It's quantum world right now.
So do you think that, let's say you ran in the United States, your party were successful?
Well, no. My idea is brewing, but my idea is that expecting from working together, and that what is missing, and that has been missing for decade, and expecting now with something changing, that's a delusion. I don't expect that to happen. It has to be forced. I think there is a chance that maybe a third force, maybe not even a party, a movement, would be enough to make both party minority. Neither party is majority. And that's not, doesn't require a lot. It requires maybe 5, 6 seats. Wasn't a minority, they will have to start talking to those people, tracking them. Those people would become like a mediator, family counselor. But that's only one.
Is there anything like that going on right now?
Well, I don't see anything like that going on. Because what I see, everybody who speaks about third party in all terms. Like we want a president, Bernie Sanders, or say that's not going to happen. Again, people have to be realistic. There is no chance the third party president will be any soon. But that's not the goal. If you take this off the table, that's not the goal. The goal changes. The tactics changes. Now, in this election, last election, if Jill Stein, for example, would say to her supporters 2 weeks before, she would say, the country is more important than I. Don't vote for me. Vote for Hillary. That's it. Hillary would become the president. That small layer of people actually can decide who will be the president. For math. First, those people should find each other, start talking to each other. Again, the perception is a party to be powerful should be massive. That's wrong. You have to be powerful, be too big to be powerful, you know? So, I don't know. But I definitely want to move ahead.
How long have you been teaching here for?
10 years, it's too much. I usually change my career every 5 years or so.
What were you doing before physics? Yes.
I lived in a different country.
Involved in physics stuff?
Oh, well, I've been teaching all my life, of course. But I also have been managing, consulting in the field of education. Everything was related to education, one way or another. But I've been doing many different jobs in that field, not just teaching. And this is what I want to try doing again. Go beyond just teaching. But, yeah.
Luck either way.
Thank you. And this was a very I knew that this is it. More free than I usually do. I had some fun. Not just you.
Yeah, sure. Thank you for making dry subject at times fun.
Not because I wanted to do it. It just happens. That's it.
you.
This is it? Yeah, this is it. At least we're fortunate to have been there for it. Yeah, are you going to do the homework?